Okay, so this is the final video in our integration topic, and hence the final video in the calculus area of study in Unit 3 for Maths Methods. So here we want to look at some applications of integration, and we're just going to look at a series of examples that cover a number of different applications. So the first application is around rates of change. Okay, so we've already talked about, and obviously a lot of these applications connect to the applications of differentiation. So we've looked at rates of change in the context of differentiation. So differentiating allows us to find the rate. And so therefore, if we're given the rate, we can get back to the original relationship using anti-differentiation. So it's just essentially taking those applications we're familiar with and reversing them. So here we have a full tank containing 350 litres of water starts to leak at a rate of 10,000 over t plus 20 squared litres per minute. Find how long it takes for the tank to empty. Okay, so essentially we've been given the rate, okay, litres per minute, the rate of volume per time, dV dt. Okay, now what we need to be really careful about here is that it is leaking at this rate. So dV dt is going to be negative 10,000 over t plus 20 squared. Okay, so be careful about that. All right, so we know dV dt is negative 10,000 over t plus 20 squared. Find how long it takes for the tank to empty. So we want to know how long, what is t, when the tank is empty, when the volume is 0. So in order to answer that, we're going to need a relationship between V and T. So we need to anti-differentiate this to get a relationship between V and T. So V is going to be the antiderivative of negative 10,000. Now I might write this as negative 10,000 T plus 20 to the negative 2 dt. So when we differentiate that, we divide by we add 1 to the power first, which makes it negative 3, and then we divide by that new power. So we're going to have negative 10,000 divided by negative 3. We would also divide by a, but in this case a is 1. Okay, and then we're going to have t plus 20. Sorry, it's not negative 3, is it? Adding 1 to that power is negative 1. So the power becomes negative 1 plus c. So we've got positive 10,000 t plus 20 to the negative 1 plus c, or that is 10,000 over t plus 20 plus c. So now we need to work out c, and we've got that information. A full tank containing 250 litres of water starts to leak. So we know when t is equal to 0, v is equal to 250. Okay, so let's put that in. 250 equals 10,000 over 20, so that's 1,000 over 2, which is 500, plus c. So 250 equals 500 plus c, and so c is going to be negative 250. Okay, so therefore, let's come back up here. So therefore, v is equal to 10,000 over t plus 20, so we've got our equation for v here, but now we know that c is negative 250. So we want to find out how long it takes for the tank to empty. Okay, so we want to know when v is equal to 0. So when v is equal to 0, sorry, t plus 20 is the equation. Okay, so that means 250 is equal to 10,000 over t plus 20. 250 times t plus 20 equals 10,000. T plus 20 is 10,000 divided by 250. So that's 1,000 divided by 25. 100 divided by 25 is 4. So 1,000 divided by 25 is going to be 40. And so t is going to be 40 minus 20. So 20, and what were the time units in? Litres per minute, so the time units are in minutes. So it's going to take 20 minutes for the tank to empty. Okay, so we can work with rates. If we're given the rate, anti-differentiate to find the original relationship. You'll need information to find the c value, which we've got here, Then once you've got your original relationship, you can answer any question that's about finding v given a certain t value or finding t given a certain v value. Okay, more specific example of rates of change, kinematics. Again, we've already looked at this, so we've already seen how differentiation can be used to connect the quantities of displacement, velocity, and acceleration, and so therefore we can work our way back up that chain using integration or anti-differentiation. So an object starts from point O and moves in a straight line. After t seconds, its velocity, v meters per second, is given by v equals 2t minus 3. Find its position, x, in terms of t. So position is displacement, okay? So to get from velocity to displacement, we're going to need to anti-differentiate, okay? So we know that x of t is going to be the antiderivative of v of t with respect to t. So that's the antiderivative of 2t minus 3 with respect to t. So that is 2t squared on 2, so t squared minus 3t plus c. Now, there needs to be information about to allow us to find c, and it's here with an object starts from O. Okay, so that means when t equals 0, the displacement equals 0. Okay, so we know that x of 0 is going to be 0 minus 0 plus c, and we know that equals 0, and so therefore c equals 0. So therefore, our displacement is t squared minus 3t. Part B, find its position after 3 seconds. So that is displacement after 3 seconds. So that's 3 squared minus 3 times 3. So 9 minus 9. So 0 meters. So it's back at O after 3 seconds. Find its average velocity in the first 3 seconds. Okay, so this is where students get average velocity wrong all the time. Okay, average velocity, now remember velocity is change in displacement over change in time. So if you want average velocity, you want average, so you want the average velocity is change in displacement over change in time. So therefore, in this case, if we want it over the first 3 seconds, we want to know how does the displacement change over the first 3 seconds compared to how the time changes over the first 3 seconds. The mistake lots of students make here is they find change in velocity over change in time, but velocity over time is acceleration. That would be average acceleration. Okay, so x of 3 is 0. We've just worked that out in part B. We already know x of 0 is 0. That's given to us in the question. The object starts from O. So we've got 0 divided by 3, and so the average velocity in the first 3 seconds is 0 meters per second. Now it's really important that you understand that that doesn't mean that the particle didn't go anywhere. It just means that the average velocity, it went as much in a positive direction as it went in a negative direction over that time, so that on average the velocity turned out to be 0. Remember, we can have negative velocity, it's about direction, so an average velocity of 0 doesn't mean it just stayed at 0 the whole time. It means it had positive velocity for a while and then it had negative velocity that's essentially cancelled that out. Find the distance travelled in the first 3 seconds. Okay, so we know that the displacement after 3 seconds is 0, but we know that that doesn't mean that the particle didn't go anywhere. So we need to be able to think about what the particle actually did, and in particular, where did it turn around? So we know that it started at O, okay, when t equals 0, and we know that it ended up back at O when t equals 3. But what did it do in that time? Where did it go? How far did it go? So we essentially need to work out, it obviously turned around in that time, so we need to work out when it turned around. So we need to know when the velocity is 0. So that is, 2t minus 3 for the velocity? When does 2t minus 3 equal 0? So 2t equals 3, t is 3 on 2. So after 3 on 2 seconds, or 1.5 seconds, the particle turned around. So we then need to know, well, where was it then? What is x of 3 on 2? What was the position after 3 on 2? So x of t is t squared minus 3t. So that's 3 on 2 squared minus 3 times 3 on 2. So that is 9 on 4 minus 9 on 2, which is 9 on 4 minus 18 on 4. So it's negative 9 on 4 meters. Sorry, it's just meters. And this was seconds. Okay, so actually it travels to the left. So I'm just going to move those over. So at t equals 0, it's at O. It then moves back here to a displacement of negative 9 on 4 at t equals 3 on 2, and then it comes back to O by t equals 3. Okay. Now obviously it's not looping around, it's just moving in a straight line, it's literally doing this, okay, but just to be able to see what's happening. Okay, so the distance travelled in the first 3 seconds. Okay, so the distance we can clearly see is 2 times 9 on 4. It's not negative 9 on 4, kind of negative distance. So it's 9 on 2 or 4.5 metres. So let's just make that more legible, 4.5 metres. Okay, so it went 2.25 metres away, 2.25 metres back to travel 4.5 metres in the first 3 seconds. So if we want to find the average speed in the first 3 seconds, so we've already found the average velocity was 0, but that's because it travels as much in a negative direction as it does in a positive direction, so the average velocity turns out to be 0, in the same way that the average displacement in that time is 0. But average speed is not displacement over time, it's distance over time. So we've just worked out that in the first 3 seconds we travelled 4.5 metres in 3 seconds, and so that is 1.5 metres per second is the average speed. So you don't just take the average velocity and make it positive, it's a different calculation. Okay. All right. Then we want to introduce one new concept that doesn't connect to an application of differentiation, and that's this idea of the average value of a function. Okay, so the average value, I'm just going to give you the rule and then we're sort of going to work through and verify why that's the rule. So the average value of f of x between x equals a and x equals b is given by this expression. So it's 1 over b minus a, and then it's the integral from a to b of f of x. So when we're finding the average value of a function, we're essentially finding the average y-coordinate over that interval. Okay, so what would be the average y-coordinate if we could calculate that? Okay, and we do that in this way. So what I want us to look at here is we're going to work through this example to help show one way we can understand average value, and then we'll have a look at another, well, it's not really different, another way that supports this logic as well. So here we've got a function, y equals x minus 2 all squared, okay, and obviously we're going to need to anti-differentiate that, so I'm going to expand that out. That's x squared minus 4x plus 4. And we've also got this line y equals 4. And we want to find the areas labelled area 1 and area 2. Okay, so let's focus on finding area 1. So they're obviously areas between two curves. So area 1, we need to first of all find where these points intersect as well. So let's do that. Let's do when x minus 2 all squared is equal to 4. So that's when x minus 2 is equal to plus minus 2. So x is equal to 0 or 4. So this must be 4. And obviously 0 we can see back here. Okay, so area 1 would be the integral from 0 to 4 of the top function, which in this case is y equals 4, minus the bottom function, which is, I've expanded it out already, x squared minus 4x plus 4. Okay, so let's just tidy that up before we anti-differentiate. So we're going to have negative x squared, we're going to have negative negative, so plus 4x, and we've got 4 minus 4, so the constants cancel out there. Okay, let's anti-differentiate. We're going to have negative x cubed on 3 plus 4x squared on 2, so that's plus 2x squared from 0 to 4. I haven't left myself a lot of room here to do the second one. So that's going to be negative, so 4 cubed is 64, so it's negative 64 on 3 plus 4 squared is 16 times 2 is 32, and it'll be minus 0. And so that is going to be negative 64 on 3 plus 96 on 3. So that is, oops, sorry, positive 32 on 3. Okay, let's work out A2. So A2 will be the integral from 4 to 6 of the top function this time is the quadratic, x squared minus 4x plus 4, and then we're going to subtract the bottom function, which is 4. Okay, so they cancel out. So we're finding the antiderivative of x squared minus 4x, which is pretty much what we did previously, except it's just the negatives. And we're doing that between 4 and 6. Okay, so this is going to be 64 on 3 minus, sorry, not 64, 6 cubed is 216 on 3, minus 6 squared is 36 times 2, which is 72. And then here, this one is 64 on 3 minus 32. Okay, so let's simplify a bit what we've got here. In fact, maybe let's collect together the fractions. So 216 minus 64 is 162, I think, on 3. Let me check that. 164 plus 60. No, I think, sorry, 152. Let's just check so that I don't go on there, sorry. So 152 on 3, and then we've got negative 72 minus 32, so it's negative 72 plus 32, so that will be negative 40. Obviously you could do this in a couple of different ways. Now negative 40 is clearly, sorry, I'm just checking that so it's minus 40. So minus 40 is the same as minus 120 on 3, so 152 on 3 minus 120 on 3 is 32 on 3. Okay. So what we've found is that A1 is the same as A2. Alright, that in itself doesn't mean a lot. What I then want to do is calculate the average value of f of x, which is x minus 2 all squared, so the parabola we've worked with and we can see in the graph above. We want to calculate the average value on the interval 0 to 6. Okay, so thinking about that formula for average value that we've got up the top here, so it's 1 over b minus a, and obviously a and b are 0 and 6 respectively, so it's 1 over 6 minus 0, and then it'll be the integral from 0 to 6 of f of x. Okay, so the average value, it's really important that we don't confuse average value with average rate of change or and various things. It's important that you're clear about that distinction. That's a common error. So the average value is going to be 1 over, as I said, 6 minus 0, and it's the integral from 0 to 6 of x minus 2 all squared. Okay, so that's 1/6 integral from 0 to 6. We've expanded this out already. It's that. Okay, so it's 1/6, and then that's going to be x cubed on 3 minus 2x squared plus 4x. Okay, so we're going to have 1/6. We're going to sub in 6, so it's 2/1/6 on 3 minus 2 times 36, which is 72, and plus 4 times 6, which is 24, and then we're subtracting 0. Okay, so let's see what we've got here. We've got 1/6 times, now we could do a couple of different things here again in terms of our simplification. So thinking about what's going to be easiest, I actually might multiply the 1/6 in, because that's going to make all those numbers are divisible by 6. 2/1/6 divided by 6 is 36, so that's 36 on 3, minus 72 divided by 6 is 12, and 24 divided by 6 is 4. So perhaps that's easier. And then 36 on 3 is 12, so we've got 12 minus 12 plus 4, and so we've just got 4. So we find that the average value is 4. Okay, let's go back up to the graph for a minute. So this is the average value. And what we found is that when that's the average value, this bit of area up here is the same as this bit of area down here. And that's a key idea about the average value of the function, okay? It will essentially, if you draw that line in, the area between that line and the function that's above that line will be the same as the area that's below that line. Okay, I know that's a slightly convoluted sentence. It's difficult to articulate into words. So let's have a little think a bit further about this idea of average value of a function, and that area idea is important, that you have a sense around that. So if we revisit the formula for average value of a function, the average y value is equal to 1 over b minus a times the integral from a to b of f of x. So if we rearrange that slightly by multiplying the b minus a up here, we get this. Okay? And if we think about this, now I'm sorry, some of these notations on this diagram have moved. So if we draw in the line y equal to the average value of y, so a horizontal line, if we think about this, average value of y times b minus a, so that distance there, that's b minus a. And if we multiply that by the average value of y, what we're essentially getting is this blue, the area of this blue rectangle. That's what that left-hand side corresponds to. And what the formula tells us is that the area of that blue rectangle is the same as the area under the curve. Sorry, I might leave that. It's the same as the area under the curve. So the area under the curve between A and B is that. So we know that that purple area is the same as that blue area. So what that allows us to conclude is the only way that they're different is this bit of area under here has been removed out of the rectangle and redistributed to be these bits of areas up here. So that green bit of area that's below the average value is the same as those green bits of area that are above the average value. Okay, so that's what's happening here. And again, apologies that annotation has moved, so it's just suggesting that this line is y equals the average value. So we find that the area between the curve and the average value, the area that's above the average value, is equal to the area that's below the average value. Okay, I know that's a slightly, as I said, convoluted sort of sentence. So it's really important that you've got a bit that sense of what's happening graphically with the average value. But really, what you need to think about is it's actually kind of calculating the average y value. If you were to think about between here and here, we've got all these y values, you know, this one and 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 this one twice and this one twice, and we've got all these y values, and if we were to sort of add them all, be able to somehow add up infinitely many y values and divide by the number of y values, this is the value we're going to get. That's it. On average, if we take all the y values, that's what it is. Okay, and it has this graphical application or this graphical sense in terms of the area. Okay, finally, let's just find another average value. Find the average value. Oh, sorry, it's not finally, but let's just find an average value. Average value of f of x between x equals 1 and x equals 3. So the average value of f, not the average rate of change, okay, is 1 over 3 minus 1, integral from 1 to 3 of x cubed minus 6x with respect to x. So that's half. It's going to be x to the 4 on 4 minus 6x squared on 2, so that's 3x squared from 1 to 3. So it's going to be half, subbing in 3. 3 to the power of 4, 3 cubed is 27, 3 to the 4 is 81. Minus 3 squared is 9 times 3 is 27. And then taking away 1. Okay. So again, let's work with what we've got here. We've got 81 on 4 minus 1 on 4. So that's 80 on 4, which is nice. Okay, and then we've got negative 27 minus negative 3. So that's negative 27 plus 3, which is negative 24. So we've got half. 80 on 4 is 20 minus 24. And so we've got half times negative 4. And so it's negative 2. So the average value is negative 2. If you were to think a bit about what's happening with that function, it's a cubic function, x squared minus 6, it's positive cubic. It's sort of doing this. This is positive root 6 and negative root 6. And so between 1 and 3, okay, so let's say 1 is somewhere there. Now root 6 is smaller than 3, so 3 is somewhere past here. So what we're finding though is over this span, the average y value is a negative value. Okay, so you can have negative average value of the function, that's no problem, because you can have negative y values. The whole function might sit below the x-axis. Every y value might be negative. So the average value here is negative 2. Okay, we should also note that we've actually already seen a specific example of the average value of a function, and that is average velocity. So we know that average velocity from time 1 to time 2 is given by the change in the displacement, so displacement at time 2 minus displacement at time 1 over the change in the time, so time 2 minus time 1. So we know how to calculate average velocity in this way. But if we think about average velocity as being the average value of the velocity function between time 2 and time 1, we could think about it as being using our average value formula. So 1 over t1 minus t2, sorry, t2 minus t1, integrating from t1 to t2, our velocity function. that would be using the average value formula. But then if we think about how we actually evaluate that, we would, antiderivative of velocity is displacement. And then we would sub in time 2, so x at time 2 minus the displacement at time 1. And so actually what we've got is exactly what we've been doing anyway, but we can choose to think about it as an average value of a function if that's an easier process to think through. Okay, it still turns out to be change in displacement over change in time by thinking about it as the average value of the velocity function from t equals t2, t1 to t equals t2. Okay. All right, so let's think about it for an example. So a particle moves such that its velocity is given by v of t equals 3t minus 5. Find the average velocity in the first 5 seconds. So average velocity is going to be average value of the velocity function in the first 5 seconds. So that's t equals 0 to t equals 5. So it's going to be 5 minus 0, integral from 0 to 5 of velocity. So that's 1 on 5. Integral from 0 to 5 of 3t minus 5. So antiderivative of 3t is 3t squared on 2 minus 5t. We're doing that from 0 to 5. Okay, so we're going to have 3 times 5 squared. So 3 times 5 squared is actually 75 on 2 minus 5 times 5, which is 25. And then we're taking away, it'll be 0 minus 0. Okay, so we've got 1/5 times, now 75 on 2 minus 25. 25 is 50 on 2. So 75 on 2 minus 50 on 2 is 25 on 2. And then cancelling down the 5s leaves us with 5 on 2. So the average velocity is 5 on 2. Let's get some units here. We haven't got actually any distance units in this particular question. So it's units per second. Okay, so it's distance units though. Meters per second, kilometers per second, don't know, centimeters per second. Okay. So yeah, we could do it by finding anti-differentiating first and finding the displacement function, and then subbing the 2 times into the displacement and finding change in displacement over change in time. But that's actually what this process is doing. So this is actually a more efficient way of doing that. Additionally, we don't actually have information to find the C value when we find displacement, and it actually doesn't matter what the C value is because we're finding a difference in displacement, so those C values will subtract away. But that's why it's actually easier to think it through this way, where we're actually not worrying about the plus C here in the displacement. We're just doing the substitution straight away and subtracting. Okay, so applications we've looked at so far: rates of change, more specifically kinematics. We've looked at the average value of a function, which we can also think about in the context of kinematics, but obviously we can also think about the average value of any other function. And the final application we just want to look at an example of is using the application of area. Okay, so an aircraft hangar has the cross-section illustrated. The roof has the shape of the function, so it's a parabola. So this 20 minus 0.6x squared is that parabola. Okay, and we want to find the area of the cross-section. So we're just simply doing the area under that parabola between x equals negative 15 and x equals positive 15. So we could just do the area between x equals 0 and x equals 15 and then double it. Okay, so the area is going to be 2 lots of the integral from 0 to 15 of 20 minus 0.06x squared dx. Okay, so that is 2 times, it'll be 20x minus, now 0.06 divided by 3 is 0.02 x cubed from 0 to 15. Okay, so that is 2 times. Alright, so we're going to have 20 times 15. 2 times 15 is 30, so 20 times 15 is 300, minus 0.02. So 0.02 is 2 on 100. So it's 1 on 50 multiplied by 3 cubed, 15 cubed. Actually don't know off the top of my head. 15 squared is 225, and timesing by 15 again. 5 5s are 25, 5 2s are 10, plus 2 is 12, 5 2s are 10, plus 1 is 11, 1 5 is 5, 1 2 is 2, and 1 2 is 2. So it's 5 7 3 3 3 7 5. You could also do that in your head with sort of 225 times 10 is 2,250, and then plus another half of that, so plus another 1,125. So regardless, we get 3375. It's a bit horrible. And then it's minus 0 times 0. Okay, so let's have a think about this. If we divide 3375 by 5, which would actually have just been doing 3 times 2250. So if we divide that by 5, so what I'm thinking through in my head, is when I did this times 15, I got this. Okay, but 15 is 3 times 5. So if I want to divide by 5, I actually want to think about having just done 225 times 3 rather than times 15. So 225 times 3 is 675, I think. So that's divided by 5, so dividing by 50, it'd be 67.5. Let me just check that while we're here before we go too far on. But you please don't expect that you won't need to do that level of kind of number work and fraction in a tech-free paper. Okay, so 300 minus 67.5 is 225.5, and so it's 2 lots of that. So 2 lots of 225 is 450, and 2 lots of 0.5, so it should be 451. Sorry, I've 67.5. It's not 225. It would be 232.5. My apologies. So 2 times 232 would be 464, so we're going to have 465. Now let's think about area. It's an aircraft hangar. In the axis here it tells us that X and Y, everything's in meters, so as an area it's 465 square meters. Find the volume of the hangar if it is 100 meters long, so it's simply a prism. Area of the cross section times it by the 100 will give us the volume. So volume is going to be the area times 100. So it is going to be 46500, which is 46,500 cubic meters. Okay, so applications around rates of change, applications around kinematics, which obviously are an example of rates of change, area applications, but also an understanding of average value of a function as well. So quite a lot of questions there from exercise 11J.